I need to find out.
Yeah, I mean, like, we're not. Yeah. Yeah. Right. You know what I did? I gave away water in my room, right? At least the big one. There are empty stuff, and it'll bring you to get something on the floor. I don't like, I use it right now.
All right. Okay. Hi, everyone. I hope there's also people on YouTube, or it's really lonely in here, but that's okay. So I wanted to continue talking about neural networks, and I wanted to briefly just call back to basically what you've done in physics. So this is this notebook. So I'm not going to ask you to like remember the syntax for anything of it, and it's basically the thing from Physics 180. So what we're doing here is we're saying, again, you don't really need to know the syntax, but I'm making, an x that's between -10 and 10, with kind of 100 data points in total. And then I'm making y be just f of x, which is like 2x squared plus 2x plus 1 plus some random noise. Okay, so, and there is a way to add the noise. So what they then do is, so I have my x's and y's, and then I'm making something like a training set and a test set, like from last time, right? So some pairs of XY points are going to be in the training set, and some of them are going to be in the test set. So that is the point of this line. So I now just have, a bunch of X train, Y train points, and I have a bunch of X test, Y test points. This is linked from the slides, right? So then I say, okay, like if I know that's a polynomial, there is a way to figure out the coefficients of that polynomial. And here, like the way you do it, if you so in physics, you fit like, I know, like, I think like it was like sine functions and stuff like that. And here I'm saying I want to fit a quadratic polynomial to it. So I know that the points are roughly some kind of parabola, but I don't know what parabola. I want to find out what parabola. The way I'm doing it is I'm plugging in the points X train, Y train into model.fit, where I said that it's, a degree 2 polynomial, and that'll get me the coefficients. So I can then just plot those. So if I run this, this is kind of what that's going to look like. So the data looks like this. So I made it so that it's a parabola, except when I'm computing the y, I'm also adding some randomness there. So it's not exactly a parabola, right? I then find the coefficients for this such that, okay, a new one. So I then find the coefficients for this kind of curve such that it's like, it can't be perfect, right? If it's a parabola, it cannot fit all those points exactly, but it's going to do as good a job as it can. And this is kind of what that's going to look like when I'm predicting. So this doesn't really matter that they are, but this is points from the test set. So not points that they used in order to figure out the coefficients of the parabola. And this is the parabola that they found that's the best fit. Okay. And I can look at the coefficients. So this is kind of the coefficients that it found. Okay. Which are, so I think I said 2x squared plus 2x plus 1. And I think it's it's basically saying +0 and then like 2.1, 1.9. So something like that. So let me just change it quickly so that it's like not 2, so I can see the difference. Say 5x. The model is still this. So the coefficients here, so it did not actually find the +1, but here you see that it found that it is 2x squared and it is 5x approximately. Okay, so the point is it's possible to do it. You've also seen it in physics. And that's exactly the kind of thing that we were doing last time with the faces, right? So what we had with the faces is we said we have this kind of formula, right? So this formula takes in the input, which is the pixels of the face, and it outputs 6 numbers. And the goal is to make the coefficients, so the W and the B, those are analogous to the coefficients from the equation for the parabola. The goal is to make those coefficients such that as much as possible, when I plug in, in an example from the training set, the pixels where I know the correct output, I'll get an output that roughly corresponds to what I want. So if it's person number 1, then the output that I would get is, Z1 is high and all the rest are low. Okay, it's the same principle. I have examples where I know the inputs and I know the outputs. And then I want to find the coefficients such that on my examples, it outputs what I would want. Yes.
So, in that factor, is that just telling you what the coefficients should be approximately?
No, it doesn't tell me what the coefficients should be at all, right? Sorry, you mean like in the Python?
Like 2x squared, 5x, like.
Oh, so it's not approximately. It's more like I'm saying like this is my data, and you're right that if the data is like f of x is equal to 2x squared plus 5x plus 1 plus some noise, then probably the best coefficients are, 2x squared plus 5x.
So what does the training set do in this case? Like, what is it training it like?
So I'm starting out. I'm starting out with this kind of data, right? The same as what you had in physics, right? So I'm saying, I know that like in my training set for x equals 7.5, the output is whatever this is, like 57, right? And then I know that for x equals 0, the output is like whatever, like 1.2, right? And then my goal is to say, well, I want to be able to plug in a new input and get something that follows this kind of trend, right? And that is what's been done here, right? So here, what I'm saying is, if I plug in this guy, I'll predict what's on the parabola because I figured out the formula that predicts the curve as well as possible. Yes, exactly. So the goal is, here's my training set. So I have my input examples and I have my output examples. And then the goal is to figure out a function that predicts the outputs as well as possible. Okay. So with a parabola, it's just about if I plug in a new x, can I predict a y that's approximately correct? With the faces, it's the same thing. So if I plug in new pixels here that correspond to one of the 6 people, I want for the output to be as correct as possible, meaning if it's person 1, I want for the output to be like 1, 0, 0, 0. And if the pixels correspond to person 2, I want the output to be as close as possible to 0, 1, 0, 0, 0, and so on. Make sense? Is that okay? That's not okay. Okay. So, okay. So that's what we've been doing. And what turns out, so this is kind of the training, right? So like we're trying to figure out the coefficients such that this works as well as possible. And where we stopped last time is that if you take the W's that produce the best possible outputs on the training set, in the sense that usually they predict the correct thing, you can then visualize the W's to see what they look like. And the reason this makes sense is that the way you compute Z1 is you do like X times W111, X1 times W111, and then X20 times W121, and so on. So those are basically dot products, right? Does this part make sense? So you have your big W, and then we're saying, well, like what goes into the computation of Z1? It's X1 times this plus X2 times the edge here, X20 times the edge here, and so on. So you're multiplying each pixel by the corresponding weight. That's a dot product. So you can express it by saying, well, like we do a dot product of this kind of thing. So all the W's where this is a 1, this is a 1, and this is allowed to vary, right? So then that's an interpretation of what's going on that would kind of explain why this could work. Is we're saying, well, like if you treat those W as if they were images, which you can, they're the same size as the images, right? So you just rearrange them so they look like images. Then here's what they look like, right? So the interpretation here is that a neural network that's able to classify faces like this, that's able to tell which of the 6 people is the input. What it's basically doing is it's taking the input pixels of X, and it's computing the dot product with that template, and with that template, and with that template, and with that template. And then it picks the name where X dot the template for that name is as large as possible. So in a way, kind of, if you find the best coefficients W, they would kind of correspond to, you know, the template for Baldwin, the template for Carell, and so on. Okay, so that's an interpretation. Another way of thinking about it is it's just a formula in the same way that the parabola is just a formula. Make sense? So, okay. So what do we need to know? So if you have a W that's like an array, you should be able to, like if you have kind of the exact setup, you should be able to say, okay, like this is what the template is. So this would be, for example, something like the columns of W in the setup that's there. And you need to know what it means that we're computing the dot product of the face templates with the inputs. Yes.
See, like double with one star. Does that mean like a summation of all the double?
So
This.
yeah, yes. Okay. Okay, I think the stream is back. Just in case, I'll also record. Okay. All right. By the way, did they say that there is a quiz? There is a quiz. But it just says, like, are you here? Okay. So, okay. So does that all make sense? Yeah.
So just back to the face template, is it, say that if you dot the face template with an input and that input is close to the face, then you should get the face, is that what it's like saying?
Well, no, you wouldn't get the face. So what it's saying is that the W, sorry, so I'll just check whether there is like complaints on Discord. Okay. Yeah. So what this is saying is that we can interpret the columns of the W as templates in the sense that when Z1 is highest, what that means is the dot product of the X with the Baldwin template is high. So we can then say, okay, well, like we interpret that column of W as the Baldwin column because the Baldwin output is high when that dot product is high. It's an interpretation, right? So it's not like we code it in. It's that after the fact, we can say, well, like what the math says is I'm outputting Baldwin when the dot product with that column is high. So I'll call it the Baldwin column. All right. So, okay. So that's faces. What I've shown you there was kind of like the shallowest possible neural network. So when you hear about deep learning, it's not that. So this, however, is the shallowest possible deep network. So it's the same kind of thing, except that there is what's called a hidden layer introduced. Why do we do that? There's going to be an intuition after, but one answer is it just works better. Okay, so here's what we do. So the goal is still the same. We have our inputs X and we have our output Z, and we want to just find the coefficients that make it so that when I input X with a particular face, then the Z that corresponds to that face is high and all the other Zs are low. So that's still the case. But what we do is the computation is basically the same, except we first compute the H's and we compute them the same way as we computed the Z's, right? So it's like x1 dot this plus x20 dot this plus x4096 dot this, if it goes here, right? So we compute the H's the same way we computed the Z's, but we have KH's with K something that we just decide, figure out what works best. And then we do it again. So with different W's. So before you asked like what the one here was for, well, it's that like we have one set of W's that connect the X's to the H's, and then another set of W's that connects the H's to the Z's. Okay, so it's the same computation, but it's a two-step thing. So you have a formula for computing the H's, which is expressed using this picture. And then once you've computed the H's, you have the same kind of formula that takes in the H's and computes the Z's. Okay. So again, you can think about it as just a picture that represents the algebra, right? So the algebra is the H's are like this and the Z's are like this. Yeah. No, they don't. And in fact, usually there would be more H's. Yeah. All right. So, and that just works better. So like if you do it with 6 faces, this would do a really good job in like much better than one nearest neighbor and better than the network that we had before at predicting whose face it is. And here is an intuition for why. So essentially what we had before is like we have 6 people and we want to know which one it is. And we have like one template per person. So basically we're saying like, here's a new face, like my face. Does it look like template 1 or does it look like template 2 or does it look like template 6? And based on that, you just output. So you can see how that might or might not work. Like those templates don't really look anything like faces, like they look a little bit like faces, but obviously kind of like, you know, me looking that way even is different from me looking that way, right? And, you know, like people's facial hair changes, like stuff changes, like one template is not. So one way to think about this is that we are basically allowing for there to be multiple templates per person, and they could be shared. And those are the templates that correspond to the H's, right? So we're saying I'll compare the input X by computing the dot product with as many templates as I want. So with the template that corresponds to H1 and the one that corresponds to H3 and so on. And then I'll combine the information about what the input looks like in terms of those multiple input templates in order to get my final answer. All right. So we can, again, just say, okay, so what do the templates that correspond to the H's look like? And the answer is they look kind of like this. If you actually run this. So here, what you see is some interesting things actually, right? So you see templates that kind of look like faces a lot more than what you've seen before, right? You also see that this, like, not so much a template, it's just that the coefficients that turned out to work the best for this number of templates, just it decided that the best way to predict the correct answer in the training set is to basically say, does the input look like this image? Which is kind of like the network memorizing the answer for this, right? Because there is like one particular image, obviously, that looks exactly like this one. It just copied it from the training set. So by copied, I mean that the best coefficients turned out to look like this, right? This is, and so like here, it's kind of especially blatant. Again, like I just decided that like one of the templates, I'm just going to use what I mean by decided. The best thing that works in the training set is to just say, I'm going to use this template and I'm going to compare every input to this template. And if the dot product is high, I'm going to say whose name it is, right? So this is what's sometimes called overfitting. So basically what's going on is if I allow, and here we intentionally did that. So if I allow for the network to have lots and lots and lots of templates, and the job of the coefficients is to just predict the answer in the training set, one thing you can do is just say, I'm going to have one template per input in the training set. And if the dot product between the new input and literally the image from the training set is high, I'm going to say, well, like that's this person and no that person, right? So that would work well on the training set, would not necessarily work well on new examples. And here, kind of, if you allow multiple templates, a bit of that is going on. So you might also ask why whoever Harry Potter has like a hole here. So that's just like a numerical issue. Like if you ran the thing for longer, that would go away. So again, like those are not literally copied from the training set. This is just the visualization of the coefficients that produce the best outputs, that predict the name of the person the best. It just happens automatically that the thing to do, if you have this kind of formula, like this is literally just those formulas. It turns out that the thing to do, if you have lots of H's and you're computing the output using this formula, the thing to do is to just make it so that some of the columns of W just corresponds to images in the training set. Yeah.
So is it different to train with this model as opposed to not having the hidden outputs? Like how do you do that? Because now you need to like optimize like two different like sets of weights.
I mean, they are kind of two different sets of weights, but like the computer doesn't care. Like in the same sense that like, you know, when you're doing like ax squared plus bx plus c. Well, those are like three different coefficients. Yeah.
Like,
Like the answer is like usually you just try to optimize all of them together. There is some work from so actually kind of there is like a funny connection to Hinton's Nobel Prize there, which is that it was officially given for actually the thing that you're alluding to, which is training those stage-wise. So like depending kind of determining the set of weights like in the bottom layer first and then the next layer and so on. And he did that with the Boltzmann machine, which wasn't the Nobel Prize citation. These days, people just got around to not doing it. And mostly you're just saying like, yeah, like those are like different symbols, but you can also just stick them all together into one vector, which is how people treat it. Right, so you just like take all the W's, all the B's, you just stick them together into one vector. You don't care that, you know, like you're using them differently inside the formula. But there is some work into not doing that. But yeah, like these days, again, like it might change if people come up with better algorithms and stuff. But yeah, like those are just like they happen to be represented using different letters just for convenience, like because it makes the notation nicer. Does that make sense?
if I was just curious, like, where you would start optimizing it, you can start with the bottom.
Yeah. So like all together. Yeah. So and so like I said, so like Jeff Hinton in like 2014, 2015 did start at the bottom, and kind of, you know, like the bottom, then the next one, then the next one. But these days, no, you just optimize all of them jointly in the same way that when you're fitting like ax squared plus bx plus c, like it's not like you first determine the a, then the b, then the c. You just do them all together. Okay. So all right. So that's one reason to think that kind of the hidden layer makes sense. And there is kind of like a system to this, right? So when we were talking about one nearest neighbor, what we were doing is just like matching X to all the images in the training set, right? So seeing like which image in the training set is the input the most like, and that's how we determine the output. With kind of the zero hidden layer neural network, so with this guy, what we did is we had as many templates as we have people in the training set. So 6 in the example, right? With the one hidden layer neural network, what we're saying is we have k templates. We decide how many templates we want. And that is how we proceed. So we say which of the templates and how much does the input match. And the templates, you've seen them, they really look like whole faces. You might also imagine that like you would have like templates that specialize in like nose shapes and templates that specialize in eye shapes, or facial hair, whatever, right? So that works better generally. It is also more prone to overfitting. So overfitting means that basically you like study to the test, right? So you're just saying, I'll just like memorize all the images in the training set. And, you know, I'll like when I have a new input, I'll just compare two templates, which really are just images from the training set. So that's, you know, studying to the test by like memorizing answers for, you know, previous year's exams, right? Yeah.
What is the nearest neighbor?
Nearest neighbor is the first thing that we talked about, right? So that's the so that's just saying I have a new input and I'll compare it to each image in the training set.
How about the zero layer?
So it's quite different, right? So like so zero hidden layer means we have this formula for we input the pixels and we output 6 outputs, right? So here what we're doing, one interpretation is so we have 6 templates and we're matching the X to each of the 6 templates. okay, as opposed to trying to match the new input X to every one of the possible training examples. Okay, and in a way, kind of one hidden layer is, and in a way, one hidden layer is kind of the intermediate thing, right? Where we're saying we're not comparing it to every example from the training set, but we are kind of allowing more than just 6 templates. All right. So, okay. So what you might say is, okay, so what we had so far is just like templates for the whole image. What you probably want to do is, and what people think the brain is doing, is not really kind of match, like when you're looking at the face, it's not like you have in your mind like a bunch of templates and say like, does this face look like this? Does this face look like this? And so on. You're probably looking at kind of parts. So what you probably want, and what probably is going on in the brain, and certainly in the visual cortex at the very low level, is you want to do, like, is there a corner in the image here? Is there an edge, the way you're computing it in project 2? Like, is there like a change in energy here? And so on, and then collect that information into like shapes of eyes, shapes of noses, shapes of eyebrows, and so on. And then collect that into kind of templates over templates over templates, and so on. And that kind of naturally leads to this kind of thinking. So what if we made it so that there's lots and lots of hidden layers, right? So you might imagine, if we're thinking about faces, that, in the first hidden layer, we'll look at, corners, changes in energy, stuff like that. And then in the next hidden layer, we'll collect that information into kind of higher order things like shapes of eyes. And then in the next layer, we'll do more like, where the eyes are in relation to each other, like what's the distance between them and so on, up until kind of figuring out what the face looks like and whose face it is, right? So that's kind of the intuition. The math is just, well, you keep computing hidden layers. And there's more to it than that. There's kind of fancy ways of computing hidden layers, but that's basically what deep learning is making this network with lots and lots of hidden layers and hoping that the information is going to be processed in a way that makes sense. Empirically, a lot of the time it works. So here I want to show you. So this work is from actually a while ago, but it's still valid. This is just a work on looking at a deep neural network and asking, what are the different neurons doing in the deep network? So what I mean by what are the different neurons doing is, if we're thinking about this kind of architecture, then H1 corresponds to a particular template, right? So like H1 maybe corresponds to saying, does the image look like this? And then H whatever is responsible for saying, does the image look like this? So what I want to show you is a big neural network with lots and lots of hidden layers. And I'm asking, like, what is any particular neuron doing? Meaning, when is the value of it high? Okay, so to be clear, like, what is Z1 doing? Well, Z1 is trying to detect person number 1. And then Z4 is trying to detect person number 4, and so on, right? So that's the kind of question. So how do you do that? So we are talking now about the new deep network, so meaning many hidden layers, 8. And it's trained to predict which of the class of objects is in the image. And there's like various classes of objects there. So there's like toy poodle, and there's flute, and there's forklift, and there's goldfish, and so on. And there's like actually a lot of dog breeds, which is going to come up. So like, it's not just toy poodle. Okay. So what we'll do is we'll just say, okay, like the way I'll figure out, because like before what they could do is they could just like take some coefficients and remake them into an image. That works when you're talking about the first hidden layer where the input is the pixels and the output is the hidden layer. But if you're computing the next hidden layer from the previous hidden layer, like neither of those are really images, so you can't really visualize them like this. However, what you can do is you can say, well, I'll just plug in a bunch of images into the neural network, and I'll check for every particular neuron which images make it so that the neuron is outputting a high value. So we say activates the most. So that's kind of equivalent to like sticking an electrode into like the brain of the neural network and seeing when the neurons fire, like with a cat, but less mean. Okay. So here's what that looks like. So if you look at layers, so what we're looking at here is the visualization for 16 different neurons. So each of the squares here is the top 9 images out of all the images that there are in the training set that make it so that a particular neuron in hidden layer number 3 is as high as possible. And what we see is that there is like a neuron in layer 3 that activates when it sees like orange patches. And we have another neuron in layer 3 that does yellow patches. We have another one that does like creepy eyes or like circles that look like creepy eyes and so on. Right? So if you look at layer 4, what you see is that there is a neuron where the images that make it have the highest value are like dogs with a white stripe across their face, right? And you have another one that activates the most when it sees like wheels most of the time, and another one that does these shapes. If you look at layer 5, you have a neuron that specializes in unicycles, and you have a neuron that specializes in really creepy eyes. You have one for cute dogs, and you have one for flowers, and so on, right? So the way it works is, earlier, so like in the early hidden layers, what you can do is basically just match templates. You can't really kind of match your templates to figuring out what looks like a unicycle. But if you do it a couple times, so like templates over templates over templates over templates over templates, that starts getting you to be able to compute something that's high if the input was a unicycle and low otherwise. Okay. All right, what do we need to know here? So we need to know how do the visualizations produced here. So the answer is just plug in all the possible images into the network and check which of the images make it so that that neuron has as high a value as possible. And if you have a function that computes the hidden neurons, then, like it's a straightforward Python program to get the top n images that make the neuron be as high as possible. Okay. All right. So, so this is getting kind of a little bit philosophical and a little bit not. So, like most people's first instinct, and like I'm not sure if that's your guys' instinct, because for the last couple of years, it hasn't been the case that face recognition was that hard, right? So your phone can do it. But for decades and decades, face recognition was not really possible. But at the same time, people, programmed, in C and Python and stuff like that. And there is this instinct of, well, like if I just write something that's like complicated enough, it'll figure out the shape of noses and the shape of eyes, and it's just going to be, a bunch of for loops and if statements and so on. And I think like again, like this is less and less true now, but certainly, 15 years ago, that would be people's instinct if they knew how to program and they knew that face recognition hasn't been done yet. Well, like just write a better program, right? But as it turned out, that just doesn't work. Like nobody's able to really just like sit down and write code that does it. What does work is working with a training set with examples that were given to you. One way of thinking about how that comes about is a deep neural network basically is a computer program, but it's a computer program that's flexible, right? So if you have, those 8 layers, you can think about them as, well, like what we do is we compute like F1 of X is the input, and that's your first hidden layer. And then you compute F2 of H1, and that's your second hidden layer. You compute F3 of H2, and that's your third hidden layer. And with a neural network, because you're figuring out the coefficients during training, like you have the outline of the program, right? So you're saying it's going to be 8 lines, there's going to be 8 functions, but you're saying, I don't know what those functions are. I am just going to figure out the coefficients for those functions so that I output the best thing on the training set, right? So one way to think about kind of specifically a deep network with multiple hidden layers is it's, a step-by-step process where you're saying, I'll have this program with this many steps, but I don't know what the steps are. I'll just figure them out so that I get the right output most of the time. Okay. So you can just think about that like that. So people sometimes call the hidden layers features. So features would be, does it look like a unicycle? Or does it look like a particular template? And what we're saying is we're learning, by learning, I mean, we're just like adjusting the coefficients in such a way that those functions compute something that makes sense. Right? And that's like one way of thinking about deep neural networks is you're writing a template for a program, but you're not saying what the program is because you don't know, because you can't figure out what the program should be. And you're just saying, well, like here's the training set, adjust my program, which looks like this. So adjust the F1, F2, F3, and so on, so that I get the right output. And then kind of the interpretation after the fact, so kind of visualizations like this, they just suggest that this works. They suggest that, F4, which computed layer 5, actually was computing something that makes sense because it turns out that one of the outputs in, layer 5 is, corresponds to dogs like this, meaning, that output is high if the input down below was a dog. Okay. So, like how is this different from Python? And how is it similar to Python? So this is a slide from Ilya Sutskever, who what year? So we went to grad school together, and like then was the chief science officer for OpenAI. Then weird things happened. Anyway, he's doing okay. Yes. Yeah. You don't. So what you know, so the question was like, how do we know what we want from each layer? And the answer is we don't, right? So like if you think about this example, we can interpret after the fact saying, oh, like, like the W's that correspond to like X times W is H1, that's like a template over X, but that's an interpretation. Really what it is like we have this formula for computing the Z's. Well, like you first compute the H's, then you compute the Z's. And we're just saying, find me the coefficients, find me the W's and the B's, such that I get a good output most of the time. In the same way that you have like noisy points that kind of look like a parabola, and you're saying, well, like, make me a formula that approximately predicts those points. So we don't specify what we want in the earlier layers. Yeah. So if you so the question was like, would I get a different output if I ran this multiple times? The answer is it depends on the implementation exactly. So like computers are deterministic. People do usually call random.random when training those neural networks in the process of sorry, or are you asking about the parabola? Or about the network? Okay. Well, like the answer is like computers are deterministic. People do usually call random not random when they're fitting the coefficients because it turns out to be useful. Of course, if you set a random seed to something, then, you know, like you could make it so that the output is the same every time. Yeah.
So if we're trading, we don't necessarily like know how these templates are being optimized. Do we like, some of you just don't know what the templates in each hidden unit is necessarily, or what?
Yeah, you don't. And again, kind of the template thing is an interpretation after the fact, right? So really all that's happening is you have this formula. That's all it is. So we can then say, okay, like to the extent that it works, why does it work? And we can say, well, like we can kind of think of, you know, the weights that go into H1, H2, H3 as templates, and we can visualize those templates. So that looks nice. But we don't know ahead of time. Like it could be, it happens not to be, but it could be that the templates, so here we visualize the templates and they kind of look like faces. So that's nice. But there's no like flow of mathematics that says that the templates need to look anything like faces, right? So that's just like what happens to work with this particular implementation, or like what happens to arise when you run this particular implementation.
So I guess like, if you look at like a larger, like multi-layer network, if like we know what our final like Zs should be,
Yeah.
right? And we know like we know what inputs we're giving, it's just we don't know how the hidden layers are operating.
Exactly. Yeah. So usually you don't, and then there is like ways to try to figure it out after the fact. So this was like one way of doing it. So like you say, okay, I'll look at a particular hidden unit and I'll kind of I'll plug in a bunch of images into the network and see what makes the neuron as high as possible, right? But that's kind of a way of trying to figure out, okay, like it works. I now want to know why, but you're not, or at least kind of, so like that's not like, there are ways of like trying to force it to do things that make sense, but we have, so for example, if you look up convolutional networks, that's a way of specifically saying, well, like make it make sense in the sense that you know that the inputs are images, so images have particular properties, use those. But in general, yeah, like you don't know what it's going to work, how it's going to work exactly.
So the representation that is just that this template causes it such that if you give it these inputs, it causes this neuron to fire.
Right.
Okay.
So yeah, okay, all right, 12 o'clock. I will see you on Monday. Thank you.